Yeah, and we will open the material of the lecture. Так, хорошо видно, господа?
Да.
Нормально, да? Ну все, начнем тогда. So, well, today we will consider the alternative method of the synthesis of the analog microelectronics filters, which is based on so-called transconductor amplifiers. And first of all, I would like to shortly remind you about some important practical moments because of this topic. So look, on the figure you have seen the simplified version of the block diagram for the homodyne receiver. I would like to remind you about this only some moments. The question is that the carrier frequency is equal to the frequency of the local oscillator here. So it means that after the mixture here and here, we will have the signal which is shifted into the constant current and direct current. And this is the reason that for the selectivity of the spectrum for the signals, we need a low pass filtering. And this is the reason that in both hands of this structure, you have seen the low pass filter here and here, of course, the same. And the question is that if we are talking about the spectrum effective signals, the pass band for the filter will be more than 1 megahertz. It means that we need the kind of special approach, special synthesis procedure, which will coincide for these tasks. And I would like to remind you that if we are talking about the switch capacitor filter, that one of the biggest limitation is the property of the operational amplifier. You remember about it, we talked about it. And this is the problem that the frequency range where switch capacitor filters can be used is limited now on the level of, we can say, 10 megahertz or something like that. Of course, it depends on the technology, obviously that it is. But anyway, if we are talking about more or less average approach, not so financially consumptive, and it is possible to say that it is more or less plus minus 10 megahertz. If we are talking about the filtering of the signals with a higher band pass, it is necessary to use another approach. And this is the reason that today we will talk about this. So this is a motivation. You see. And some important moments concerning the application of this type filters based on transconductors. First of all, it is possible to say that it is totally analog. It is continuous time circuit, in opposite to the digital or discrete time. As I said, it is more or less oriented to high frequency applications. The question is that the transconductor corresponds to the current amplifiers, you see, and if you are talking about the current amplifier, it is not necessary to realize the very high voltage coefficient. You see, the main difference between the current amplifier and voltage amplifier, it is not necessary to realize a high voltage coefficient on the wide frequency band. And this is the reason that in general sense, в общем смысле, the current amplifier usually will have more higher working frequency range in the comparison with the voltage. You see, вот по этой причине обычно все-таки рабочий диапазон частот для усилителей тока оказывается шире, нежели чем для усилителей напряжения. Вот на этом играет. So, and here, so look. On the second figure, you see the symbol of the transconductor amplifier. It is on the left side here. And on the right side, it's equivalent presentation. It is possible to say that it is something like the operational amplifier, but as I said it is oriented to the amplification of the current instead of voltage. You see, this is the main difference. But anyway, we have the differential input stage. Also look at here, with plus and minus polarities, you see here. And we have on the output block the current source, It means that the input impedance and the output impedance of this amplifier are very high. So ideally, we can say that it is about 10 or maybe more mega ohms or something like that. So anyway, if we are talking about the characterization of a such type of amplifiers, it is possible to see that we have the functionality between the input voltages here and the output current. It is here. And of course, the parameter which is used for the characterization of a such type of amplifier is its transconductance. And this is the reason that this approach is called like the filters based on transconductance. So this is the reason. And just a second, I forgot one important detail, I think. Or maybe later, it doesn't matter. So, well, and this type of amplifiers is used for the realization of the current constant, постоянное времени. Say other words, it means that the element basis, elementная база of a such type of circuits is transconductor amplifier plus capacitors. So you can see that the time constant corresponds to the combination of the transconductance of the amplifier Gm and capacitor's value. And this is the idea of the approach, you see? То есть, другими словами, еще раз на русском повторю, чтобы на всякий случай, может быть, более аккуратно. Постоянные времени схемы реализуются на основе комбинации, собственно, величины рабочих конденсаторов и вот этой самой передаточной проводимости, которая соответствует тому или иному транскондуктивному усилителю. Вот такая вот идея. The main approach, look at here, the main approach to the synthesis procedure of filter is a so-called element simulation method. I would like to remind you that previously we have considered, and in your work also we have considered the approach which is called operational simulation method. Here we have a kind of alternative version of it. The idea is to fix the structure of the prototype. So look, fix the structure of the prototype, I mean the passive filter, yeah, the passive prototype which has the ladder circuit, and to replace each inductor by its equivalent circuit based on active microelectronics realization. So this is an idea. So it means that we need the specialized circuit which will be oriented to the realization of inductor, more precisely for the inductor impedance, but it will be based on active elements. As you can understand, on this case, we will use the transconductor amplifier. So, and it is necessary to do some theoretical basics from this point of view. Now, let's go. Let's see. Here on the figure 3, here, we have a circuit which is called gerator. The circuit which is called gerator. In Russian the same, gerator, схема называется. And you can see that it is based on connection of two transconductance amplifiers with the necessary polarity. So look, the left amplifier will have the polarity plus and the right will have the polarity minus. Or it can be vice versa, it depends on. On the right side of the figure here, you have seen the symbolic legend for this block. Once again, we will say that the input impedance is on the left and the output impedance is on the right of it. Say other words, it is node number 1 and node number 2. Okay. So let's try to analyze. let's try to analyze this circuit. Of course, we will talk about the idealization, and it means that there is no any parasitic elements inside the circuit. So in other words, we are talking about, once again, we are talking about the connection of two voltage controlled current source. So in Russian it is ITUN, you remember about it, источник тока, управляемый напряжением. Да? Вот они здесь включены встречно, вот так, соответствующей полярностью. This gives us the possibility to form the Y matrix for it. So look at here, the Y matrix is here. You know how to prepare it. And after all, for our analysis, we have to write the matrix from the Y matrix form into the A matrix. I would like to remind you that the A matrix, or this one, A matrix, is used if we consider the cascade connection of any components. And this is the reason that it is very effective if we have considered exactly this case. In our demonstration, in our analysis, yes, it will be, and this is the reason that it is better to realize the results using the A matrix. This is the reason that we have to take the handbook and see, so the description of the elements of the Y and A matrix, and you can see here the interface between them. The A matrix can be represented using the Y parameters on this form. After all, after the substitution of the Y matrix into this block, we will have the results. So look at here, the A matrix corresponds to this right side here. So in other words, it is possible to say that the main diagonal of the A matrix for the generator is equal to 0, and we have only non-diagonal elements here and here, on the upper and of the bottom. So, well, what does it mean? What does it mean? So, look, in general case, we have the following equation for the input impedance of the structure. And it will be possible to see how it will be changed for the generator. So, look, the input impedance for the two poles using the A matrix corresponds to the following equation. One. So look at here to this one. You can see that in our case we have the 0 and 0 in this position, so it means that A11 and A22 will be equal to 0, and we will have these formulas. Say other words, yeah, by the way, so it is obviously, but anyway, ZL corresponds to the terminal impedance of the generator. In accordance with our symbols, it means that it is the impedance which is here, from the node number 2 into the ground, yeah? You see what here? Here is ZL. So it means that if the amplifiers of the circuit is identical, so it means that the transconductance of the first and of the second equal, and this is the reason that input impedance will be equal to this formula. From this equation, it is possible to see that the generator is a so-called impedance inverter. Say other words, if the terminal here is the terminal impedance is of the capacitor type, as you can see here, like that. So the input impedance will correspond to the inductor. Say other words, the reactance will be changed into the opposite. This is the reason that usually the generator is called as the impedance inverter circuit. And the coefficient of this inversion depends on, as you can see here, depends on the transconductor parameter. In our case, it corresponds to the square of Gm. So, say other words, on this configuration, it will be possible to realize the inductor with these values. So, look at here. Say other words, we have the element like this. So, is it any questions for this moment? Is it okay? Hello?
Yes, okay.
No, let's go. So it means that from the equivalent point of view, it is possible to conclude that on this case, we have the realization of the grounded inductor in accordance with these figures. So you see, as we said, on the right side here, on the second node, we add the capacitor. So it means that on the first node here and here, we have the inductor. The question is, so obviously that it works well. The question is, will it be possible using the same approach to realize the floating inductor? How to do it? Once again, it is necessary to do some analysis. So let's go. Let's go to see how it is. First of all, we can consider the figure number 5, where there is the cascade combination of 3 components. So look, this is the first generator. This is the first generator on the left side. On the middle side, we have the capacitor, and on the right side, we have the second generator. So each of these components will have their own A matrix. Now let's go. So look, the first bracket corresponds, the first bracket corresponds to the A matrix of the first generator. The second brackets correspond to the A matrix of the capacitor. And the last brackets, or this one, correspond to the A matrix of the second generator, of this part. So it means that after the multiplication of all of these elements, we have the following result. So look into this figure, into this formula, and for your understanding, the first generator is marked by the index 1 here and here, and the second generator, or this one, is marked by the index 2 here and here. So after the multiplication, we have the results. And by the way, this is the reason that we have used the A matrix instead of Y matrix. You see, it is a rather simple thing to multiply the A matrix if we are talking about the cascade configuration of the circuit. You see, exactly as in our case. Exactly, you see. And this is the reason that it was necessary to transform the Y matrix of the generator into its A matrix counterpart now. So anyway, if we have the results, it is possible to substitute into the matrix, the A matrix for each element, like here. We will do it. So, and after this substitution, we have the results like that. And if we are talking about the ideal case when the amplifiers and say the generators are identical, so it means that we have the results. And if we compare the obtained results with the second one for the A matrix of the passive element, for the floating inductor, we have seen that it is exactly the same. Look. And once again, it is possible to say that this structure, the structure shown in figure 5, this structure corresponds to the inductor with this value. Corresponds to the inductor with this value. So look at here. Okay. So it means that if we are talking about the main approach for the realization of the high order filter, it can be realized using the reactance transformation method once again. So I would like to remind you that on this case, we have the prototype like this. Once again, you see the fragment of the ladder structure, as we have done it using the low pass filter. So it means that the question is how to implement inductors L1 and L2. And as you can understand, it is possible to calculate the parameter of the transconductor amplifier GM and the capacitor which is on the output of the generator and introduce it and substitute each inductor of the prototype by these active elements. And this is the reason that, of course, we will have the structure like that. The first block, the first generator, so this first block corresponds to the inductor L1. So the capacitor which are marked by the ball lines corresponds to the C1 and C2 from this side and from this side. And the second inductor corresponds to the second generator block like that. You see, there is one misprint on the figure. No, you see, the problem is that I am very limited in the time just now, and it was not the time for change it. Of course, here is not C1. You see, this is the capacitor which corresponds to the inductor L1, and this is the capacitor which corresponds to the inductor L2. No, you know.
Alexander,
No.
How should we choose the values of capacitors between the generators, and can we somehow utilize the fact that we can produce the capacitances very close to each other?
First of all, once again, it is necessary to see this general equation. It means that after the solution of the approximation problem, after the choose of the prototype, we have the value of L. So it is known. And the main question, which value can be obtained for the GM factor? You see? And this is the main question. And after all, I think about 10 minutes or maybe 5 minutes, we will consider how to realize the transconductor amplifier, and the question is how to analyze it and to obtain the value of this parameter GM. You see, and the question can be, I would like to say, replayed, as it is possible to say, ну, как бы переформулирован. Вот тут надо не величину конденсатора выбирать, а вот каким образом правильно выбрать схему усилителя, чтобы получить соответствующее по возможности большое значение GM. Вот так вот надо вопрос ставить, понимаете? Конденсатор здесь не является узким местом.
То есть есть какие-то конкретные, ну, что ли, как-то, ну, величины GM, которые там достижимы и возможны? Которые,
да, совершенно справедливо, которые являются достижимыми, потому что, в общем, это все зависит и от потребляемой мощности, там, от всего. Это, в общем, это основной вопрос. А как всегда, конденсаторы, видите, должны быть в пределах единиц пикофарад. То есть не менее, собственно говоря. То есть ориентируясь на стандартные тут, так сказать, ну, линейки, которые комок технологии обеспечивает, но это, естественно, от единиц до десятков пик. Вот надо за эти пределы не выходить. Но это совершенно общая рекомендация. Она, вот, в общем, не является здесь, как бы, так сказать, чем-то замечательным таким, понимаете?
Понятно. Спасибо.
Так, ну давайте дальше двигаемся. So, it means that after this substitution we have the structure like that. We have the structure like that. And the main question is how to realize the good, and we can say effective transconductance amplifier, this one. And here I would like to demonstrate you some possible realizations, and it is the approach, this is the approaches which are practically used, and we have a number of realizations based on this circuits, and you can see that in general the main problem is how to organize the input stage, how to organize its gain factor and so on, and it depends on the configuration of the elements of the input stage, and you can see a number of it. The problem is that each of these structure will have their own non-linear properties. And the noise properties as well, and sometimes it is the kind of contradictions, and if we have a good non-linearity, we have simultaneously the bad noise, and it is possible to understand this trade-off very simple, very simply. The question is that normally to eliminate nonlinear distortion, we have to increase the current. Obviously, if we are increasing the current, so the noise will be, of course, increase as well. So on this case, it is necessary to have the kind of optimal solution. And from this point of view, once again, the theory of optimization is very important, especially for such types of tasks. So anyway, in our realization, we have used the design which is proposed in figure 9. It is our ideas, and it works well. And of course, we have realized some practical things based on this, and based on this circuit. And at the end of the today lesson, I would like to demonstrate you some photos concerning it, and say some words about the characteristics. But anyway, of course, each of these blocks can be analyzed, and we have the formulas, expressions for the GM factor, and totally analyzed all of this and have some information about the noise, nonlinear distortions, and so on and so on. The simplest structure of the transconductors amplifier, it is the classical, I would like to say, classical differential stage. So let's try to analyze it, and we'll see how it works from the point of view of its transconductance. So the generalized structure of the differential cascade is here, and you can see mainly it consists of 3 blocks. The first block here, it is the stable current source. It is the bias, say basics of the transconductor stage. So amplification stage and the terminal. The terminal corresponds to the current mirror, and you can see the ratio of the left and of the right side of the current mirror is 1:1. So we will suppose, that both transistors of the left and of the right side, the T1 and T2, are working on the saturation regime. And this is the reason that we will start from the current, current of the left and of the right sides, left and of the right hands of the structure. And after all, the idea is to analyze the output current, which can be determined as the difference of the current 1 and current 2 on the left and on the right side of the circuit. Now let's go. If we are talking about the saturation, so it means that the drain current of each transistor will be equal to this and to this equation, where K is the standard CMOS parameter, depends on the mobility. Technological parameters and the size of the transistor gate. So it means that the output current, as I said it is the difference between the left and the right currents, I1 minus I2, and from the input side, we have the voltage, which is equal to the difference of the gate source voltages of the first and of the second transistor, like that. So this is the general things, this one and this one, and we can use these formulas to analyze and to obtain the result. So first of all, it is necessary to rewrite the formulas for the current, and you can see to formulate the expression for the input voltages for the first and for the second. So it means that from the first line we have something like that. Coming back to the differential voltage on the input, we have the difference between two radicals like that, or after the multiplication for this and for this value, we have this difference. Okay. For the output current, it is possible to present it like here with these two brackets, and to introduce the previous formula into this one. Instead of the first bracket, we can use the previous formulas. After all, we will rewrite it like here. So, and after the squaring of these formulas, we have so this result. Just now, it is necessary to come back to the structure, to the circuit, and it is possible to conclude that the sum of the currents of the left and of the right sides of the amplifier will be equal into the basic, into the bias current of the amplifier. So it means that I1 plus I2 will be equal to this value, and we will use it. So you can see that it is, and it will be possible to substitute it into the previous equation. It means that the output current will be equal to this value. So, and possibly the last step of the analysis, it is necessary to calculate the second term here. For this reason, we will square the left and the right sides of the previous equation and use it like here. It will be possible to substitute this value instead of radicals. Instead of this one, we will use this difference here. So, and after all, it will be possible to rewrite like this one. So, some conclusion from this point of view. So, what we have? First of all, it is possible to say that the main parameter, say in our case, it is Gm, transconductance, is equal to this value. Just now we talked about the possibility of the calculation for the elements, and I said you that there will be a big problem with the current and with the power consumption. So you can see from this, if we need to increase the main factor, it will be necessary first of all to increase these values, you see, and the problem is that it will be necessary to increase the size of the transistor, for example here, to increase the parameter of it, or it is necessary to increase the current. Both cases are not so optimal, and of course we need some additional, I would like to say, schematic level solutions for this, and this is the reason that we have, of course, a number of amplifiers, as I demonstrated you, and this is the reason that, of course, the classical differential stage is used very, very seldom. It's very seldom. Coming back to the question of the nonlinear distortion, it is possible to see here that it depends on the second term of this formula, I mean this value here. And once again, if we would like to realize the structure with a low nonlinear distortion, it is necessary to minimize this. It is necessary to minimize this term. It is, once again, it means that the current should be increased. So this is the problem. But anyway, coming back to another structure, it is possible to demonstrate that this modern design, of course, oriented to the nonlinear distortion compensation, and this is the reason that the circuits are widely used practically. Now, for example, coming back to our own design, I would like to say some words. The question is that we have combined here two regimes of the transistor here on the input stage. You see, generally speaking, the first transistors are working on this pair, are working in saturation. This is the first position, and the second pair of the transistor here is on the linear regime. It is possible to demonstrate that the sign of the nonlinear distortions for the saturation and for the linear regimes are opposite. Так, господа, я прошу прощения, тут придется на телефон ответить. Сейчас, одну секунду. Yeah, so, and if the sign of the nonlinear distortion, especially if we are talking about the third harmonic, are opposite, it is possible to realize a compensation circuit on the second stage of the transconductor amplifier. And this is the reason that as summary, the nonlinear distortion will be less than for the first stage. Ну, вот такая вот идея. A little bit later I will demonstrate you so the photo of this amplifier, and we will talk something else about it. So let's go. The next moment is the tunability of the filter. I would like to remind you that one of the main advantage of the switch capacitor design is that we have a very, very high accuracy of the realization. You remember about it. And we have demonstrated that it will be possible to have the error of the time constant realization more than about 1% or maybe less than 1%. And it is excellent result. It is very good result. The question is it possible to realize the same situation here? Unfortunately, it is not possible because the idea of the switch capacitor design is to realize the ratio of two elements. Say other words, it is the kind of tabulation of the error on this case. Here we have the realization of the time constant for the circuit, which is based on another type of elements.
Извините, Вера Владимировна спрашивает.
And this is the problem, that it will not be possible to realize the high accuracy time constant. This is the reason that we have to use the special tuning system. We have to use the special tuning system if we need the accurate realization of the amplitude response. And here you see the block diagram, the structure of the tuning system, which is widely used for this task. So look, the output parameter is here. It is the control voltage. It is the control voltage, and in general, tuning system corresponds to the PLL. As you can see, it is the phase lock loop, FAPCH in Russian, Systema FAPCH. And the idea is, you can see that there is the special block here. It is the voltage control oscillator. But the question is that its elements, we can say more precisely, its component, which are frequency dependent, will be or should be realized using the same approach like it is done in the main tunable filter. It means that if we have the same technological line, the results for the accuracy for this voltage control oscillator and for the filter will be more or less the same. Say other words, the percentage of the error for the filter and for this voltage control oscillator will be more or less the same. And it means that if we have the information about the output frequency for this voltage control oscillator, and we have the possibility to change this frequency, say other words, to tune it, it will be equivalently the same if we realize the tunability of the filter. And from this point of view, it is possible to say that this approach is good working. And once again, a little bit later, I will demonstrate you results, how it is. Just now, some words about the structure. You can see that in accordance with the PLL structure, we have the reference generator, it is the stable generator, and maybe it is the kind of digital clock or something like that. But the question is that the output frequency of the voltage control oscillator should be the same as for the reference. And the error between these frequencies corresponds to the error which can be compensated using the tuning system for the filter, which is tunable. So it means that we have the signal of error after the phase detector, it is here, and after the smoothing filter, here on the output we will have the control voltage. Two additional blocks. If we are talking about the digital phase detector, or we can say more precisely impulse phase detector, it is necessary to use here the special formation circuit to transform the signal from the output of voltage control oscillator to the digital form. It is usually it can be done using the simple inverter, digital inverter, and so it means that the output of each of them here and here will have the pulses. And after that, we have, after the phase detector, the error signal. So, and there is only one there is only one limitation. In general, the system like that will have the possibility to compensate the frequency error. Unfortunately, if we are talking about the realization of the poles and zeros of the transfer function, it is necessary to remind that every poles and zeros will have two parameters, not only the frequency, but the quality factor as well. We have talked about it, and this is the reason that on the difficult cases, it is necessary to realize two tuning systems. The first one with the orientation into the frequency compensation, and the second for the orientation to the amplitude compensation. Say other words, it should be a kind of gain control system. In Russian we can say, если первая система это FAB, то вторая что-то похожее на ARO. То есть если вот какие-то сложные вот такие дела возникают, то приходится две вот такие петли ставить. Но на самом деле редко, в общем-то, когда так делают. Пожалуй, это ни к чему. So, and just now I would like to demonstrate you some results, some moments. Where is it? So, ага. Так, видно? Посмотрите, пожалуйста, сейчас. Так, господа, видно сейчас?
Нет, не видно.
Картинки нет?
Нет.
Так, вот сейчас как?
Сейчас видно.
Видно, да? Так, so, well, let's go. So this is the practical results. You remember that we have finalized 1 week ago our lesson by some photos and so on devoted to the realization of switch capacitor filter. Here you can see the realization of the transconductor based. So look, on the photo here, there is two sides, the left one and the right side, here, the right side. So the left one, this one, it is exactly the filter, and the right side, it is the tuning system. And you can see that we have realized the low-pass Bessel filter with the cutoff frequency 1 MHz. So, and it is very cheap because we have used very standard CMOS technology, but it was sufficient for this realization. And the structure of the filter is here. First of all, one important, we can say, practical recommendation. It is necessary to use the balanced structure. Look at here. It is the balanced structure because Once again, it is the problem of the nonlinear distortion. I would like to remind you that if we are talking about the balance structure, so it means that the second order harmonics will be compensated because of the balance nature of the circuit, and this is the reason that this approach is practically used. And look at to the terminal block. This is the realization of the resistor here, and this is the realization of the resistor here on the input and on the output. Generators are inside it, this one and this one. It is demonstrated symbolically, but we have considered each circuitry just now. And so the last important moment is the first block. If we are talking, because we are talking about the current amplifier, it is necessary to change the basis of the proceedings. And from this point of view, it is necessary to change the voltage input signal into the current form. Необходимо перевести входное напряжение к виду тока. And this is the reason that it is necessary to use additional block here. It is transconductor amplifier with the same structure as the filter. And this is the reason that here we have one additional extra block. But anyway, it works well. And look at here, we have a number of characteristics here. Yeah, on this slide. First of all, coming back to the question about the nonlinear distortion, you can see the screenshot from the spectrum analyzer, and this is the main harmonic, and this is the nonlinear distortion harmonic. You see, it is here, and it is possible to calculate the nonlinearity. On the right figure. On the right figure, there is the noise spectrum, and here is the results of the spectrum analyzer, and the second line corresponds to our estimation, to our calculation. You can see that it is more or less similar, and the same situation with the amplitude response. You see, the filter was realized using the Bessel approximation, and so you can see here very smooth characteristic, very smooth amplitude response. It is here, and it is possible to see how it can be changed. Once again, it is a kind of, we can say, a kind of tunability of the filter. So, and the total characteristics are here. So look at, for your example, you can understand what's that. And one important detail is the voltage control. You can see how it can be changed. Yeah. For the minimum and for the maximum. So, now I think more or less that's all. We have finalized the material, and your questions, please.
Excuse me, I have one. Can you hear me?
No.
Hello, excuse me. Can you please hear me?
Yes.
Yes, please.
Okay, sorry. I was just asking about, will you please form like a special folder on the distant learning site so we can upload our coursework, or we should send by email the final version?
Yes, yeah, of course. Yeah, that's so by email, I think.
By email. Okay, thank you. That's all. I don't have other questions. Thank you so much.
Yeah.
Можно я по-русски спрошу? Вот вы, когда заходила речь о входной части, там, где еще была такая симметричная схема, балансная схема, я не совсем понял, это была входная часть именно всего фильтра или транскондуктивная?
Картинка видна вам сейчас?
Да.
Ну вот речь идет о чем? А вот
это.
Ну.
Ага.
Ну, еще раз вопрос.
Ну, то есть вот эта вот входная часть входной блок был нужен для того, чтобы перевести входное напряжение в входной ток, так? И
Да-да.
потом идет вся остальная структура уже самого фильтра
Да.
из конденсаторов и транскондуктивных усилителей.
Вот смотрите, вот здесь вот за счет вот такой вот я сейчас показываю курсором, вот такой стопроцентной обратной связи на основе одного усилителя можно реализовать соответствующий набор резисторов, то есть вот это входное сопротивление, ну или точнее их два, естественно, поскольку есть верхнее и нижнее плечо, да, это же балансная структура как бы, да? Значит, поэтому вот такой блок реализует набор сопротивления по входу, вот такой же вот блок реализует сопротивление по выходу, а серединочку, вот собственно сами индуктивные элементы, реализуют вот эту вот часть. Ну а заземленные конденсаторы, вот они. Вот я их сейчас показываю. C1, C4, C7, C2, C5, C8.
Хорошо.
А в серединке индуктивности взвешенные, которые, вот взвешенные индуктивности, floating inductors, они вот реализованы как раз на основе гераторных структур.
А с помощью вот этой гераторной структуры можно другие типы фильтров тоже, там, пулсовой или высоких частот реализовать?
Это же зависит не от гератора, это зависит от решения задачи аппроксимации. Точно так же, как все остальное. Естественно, общий подход остается такой же. То есть реализовываем соответствующую аппроксимацию, после этого выбираем прототип лестничного типа, да, если необходимо, осуществляем реактансное преобразование, ну а дальше вот, собственно говоря, основная идея понятна. Надо сохранить высокую или низкую, простите, чувствительность, да. Чтобы сохранить низкую чувствительность, надо сохранить соответствующую лестничную структуру, поэтому ее опять же сохраняем, а индуктивности заменяем вот такими эквивалентными структурами, но только на основе активных компонентов, естественно, ну поскольку под комоп реализацию все это выводим.
Хорошо, спасибо.
Угу. Так, ну что, вернемся давайте тогда к нам обратно. Так, so, yeah, first of all, I would like to stop the recording, just a moment. Потом, oops.